Unit 1.2 practice problems. The mass spectrum of the element antimony is likely represented by which of the following? So first we need to figure out how much antimony weighs on average. And so I'm going to go ahead and look, and I see that antimony has a mass of 121.8 approximately. So I can go ahead and eliminate any that are not going to remotely get me there. So A is going to be eliminated immediately because all of my mass is at 122, which is more. Then D I can also immediately eliminate, as I'm looking for, again, 121.8. This is going to get me pretty close to 124, so that's not going to be helpful. So D can be eliminated as well. Then I'm left between C and B. Without doing any math, again, I'm looking for me to be pretty close to directly in the middle between 121 and 121 and 122. So something around there. We have 121 and 123 here. So we're going to be somewhere over here. We are slightly more abundant in 121. So we're going to get ever so closer to that range. So that's looking good. Over here though, again, I'm looking like I'm going to be skewed more to the right, be heavier, and so that's not going to be a good answer choice. So answer choice B is going to get me the closest to 121.8, or approximately 122, and so that is the answer choice that I will be choosing. Which of the following elements has the mass spectra represented opposite? So we have 4 options here. We have niobium, molybdenum, uranium, and californium. So I'm gonna go ahead and find all of those there and find out what their masses are so that I can figure out if this mass spectra makes sense for all of them. So first up, we have niobium, which is going to be element number 41 with a mass of 92.91. Then we have molybdenum. Molybdenum has a mass of 95.94. Then we have uranium. Uranium has a mass of 238. And we have californium, which is going to have a mass of approximately 251. I can see that my masses are going to be between 92 and 100. And so I can go ahead and eliminate uranium and californium because they are nowhere near that mass. And so that's definitely not going to be the element represented there. Then between niobium and molybdenum, I'm going to look to see where I am. I have a wide range here where I'm again between 92 and 100. I am over 92, and a lot of my elements are over 92 as well. So that means I'm not going to really be very close to 92. Instead, I will end up kind of somewhere in the middle of this range. And so that is going to be best represented by molybdenum's mass of 95.94. Again, just because I have so many options here between of all of the elements and isotopes that I have present here. So answer choice B is going to be my best answer choice. The mass spectrum of a sample of a pure element is shown below. Based off of the data, the peak at 26 AMU represents an isotope with which of the following elements? Okay, so we have mass of 26. We're going to mostly be right around 24 as our overall mass there. So aluminum would be has a mass of normally like right around 27. Then we have magnesium with a mass of 24. We have iron with a mass of 56. And titanium with a mass of 48. So mathematically, these are all going to work out a little bit differently. So aluminum with 13 neutrons, and again, we're looking at the specific isotope where we have 26 as our mass here. 13 minus, or 26 minus 13, that would give me 13 protons, which would be aluminum. Magnesium with 26, so 26 minus 14 is going to give me 12 protons, which is the correct number of protons. Then we get like a little bit iffy here. So here we have iron with typically a mass of 56, but if I have 26 neutrons, that's 0 protons, and so that's not iron at all. And then same thing with titanium here. I have 26 neutrons present. If my entire atomic mass is 26, that would mean I would have 0 protons, which means I'm not going to be iron or titanium. So that's not going to work out as well. And if you subtracted those, so if you had done 56 minus 26, that would give you 30, which is the wrong number of protons anyway. And so again, those can immediately be discarded. So here we're dealing with the correct number of protons and the correct number of neutrons to add up to that 26 number there. So the differentiating thing is going to be looking at the actual periodic table to see what mass spectra would match this mass spectra the best. And so again, aluminum has a mass spectra that ends up where we have our mass being approximately 27. We don't have any masses where we're above 27 at all. So that cannot be, this cannot be aluminum's mass spectra if we don't even reach the average mass of aluminum there. So aluminum's going to go ahead and be eliminated as well. And then we are left with just magnesium with a neutron count of 14, proton count of 12, and our average mass being closest to 24, which we can see reflected in this mass spectra here. The elements iodine and tellurium have similar average atomic masses. A sample that was believed to be a mixture of iodine and tellurium was run through a mass spectrometer, resulting in the data opposite. All of the following statements are true. Which one would be the best basis for concluding that the sample was actually pure tellurium? So I can see that, again, my mass specs are going to be similar. So tellurium, we have a mass of approximately 127.6. And for iodine, we have a mass of 126.9. And so they are very similar. And this is one of the examples where mass does not increase as we go from left to right across the periodic table, even though the number of protons increases. So this is one of those prime examples there. So looking at the mass spectra data, I cannot conclude anything about the purity of the sample for whether it's tellurium or iodine based off of the charges. The charges are not evident at all within this mass spectra data, so answer choice A is not going to be a good answer choice. Answer choice B, that would be relative abundance in the universe, and that is not helpful in terms of abundance within a particular sample. So B is also not going to be helpful. Then we have answer choice C, which states that iodine consists of only one occurring naturally occurring isotope with 74 neutrons, whereas tellurium has more than one isotope. That is a helpful thing because I can see that there are definitely a lot of isotopes here. If we have 74 neutrons as my typical iodine isotope here, so 74 plus the number of protons that I have there, which is 53. And so that is going to get me to that 127 value. And 127 is not present at all within this data set. So that is concerning for any amount of iodine being present at all. Since the only naturally occurring isotope of iodine is 127, and we don't have any at all, that's looking like I really don't have a lot of iodine, if any at all. And so I'm going to go ahead and look at answer choice D to see whether or not C is my best answer choice. Answer choice D says iodine has a higher first ionization energy than tellurium does. That cannot be determined based off of mass spec data, so that is not going to be helpful at all. Instead, answer choice C, which tells us that if we don't see any isotopes with a mass of 127, we have a problem, and we don't have iodine really present at all, is going to be my best answer choice. So answer choice C is what I would select. The mass spectrum for element X is presented in the diagram opposite. Based off of the spectrum, which of the following can be concluded about element X? So element X, we can see that we have our lower band at 90 and our upper band at 96. And we are very heavily weighted toward 90 as our average mass over here. Let's go ahead and look. So answer choice A says that X is a transition metal, and each peak represents an oxidation state for the metal. That is incredibly incorrect. So that one's going to be tossed out immediately. Again, mass spectra is just finding out the relative abundance of the different types of isotopes that are represented within a sample. My oxidative states are not going to come into play with this at all. X contains 5 electron sublevels. Again, electrons not coming into play with this at all. This is just strictly about mass, and electrons are not going to be represented in a mass spectra at all. And then it says that the atomic mass for X is 90. That would be true if there was only one peak here, but I don't only have one peak, so I'm definitely going to be over 90 since, again, I'm between 90 and 96 here as my upper and lower band limit. And then I am mostly going to be closer to that 90, just based off of the relative abundances of everything, but I'm definitely not exactly 90. And then answer choice D states that the atomic mass of X is going to be between 90 and 92. Now I said that we had an upper limit of 96 and a lower limit of 90. So maybe you think, oh, that's not right either, because it's between 90 and 96. But again, we're seeing that the vast majority of the sample of element X is on that left-hand side, is closer to 90. And so mathematically, we are going to be much more heavily weighted toward this left-hand side. And so between 90 and 92 is a good guess for how much that element is going to weigh on average. So answer choice D is going to be my final answer choice.